The Internals of Postgres. Chapter 6, Vacuum Processing. Vacuum processing is a maintenance process that facilitates the persistent operation of Postgres. Its two main tasks are removing dead tuples and the freezing transaction IDs, both of which are briefly mentioned in section 510. To remove dead tuples, vacuum processing provides two modes: concurrent vacuum and full vacuum. Concurrent vacuum, often simply called vacuum, removes dead tuples for each page of the table file, and other transactions can read the table while this process is running. In contrast, full vacuum removes dead tuples and defragments live tuples, the whole file, and other transactions cannot access tables while full vacuum is running. Despite the fact that vacuum processing is essential for Postgres, improving its functionality has been slow compared to other functions. For example, until version 8.0, this process had to be executed manually with a pSQL utility or using the cron daemon. It was automated in 2005 when the auto vacuum daemon was implemented. Since vacuum processing involves scanning whole tables, it is a costly process. In version 8.4, 2009, the visibility map, VM, was introduced to improve the efficiency of removing dead tuples. In version 9.6, 2016, the freeze process was improved by enhancing the visibility map. Section 6.1 outlines the concurrent vacuum process. Then the subsequent sections describe the following: visibility map, freeze processing, removing unnecessary clog files, auto vacuum daemon, full vacuum. 6.1 Outline of concurrent vacuum. Vacuum processing performs the following tasks for specified tables or all tables in the database. 1. Removing dead tuples. Remove dead tuples and defragment live tuples for each page. Remove index tuples that point to dead tuples. 2. Freezing old transaction IDs. Freeze old transaction IDs of tuples if necessary. Update frozen transaction ID related system catalogs, the PG database and PG class. Remove unnecessary parts of the clog if possible. 3rd, others. Update the freeze space map and visibility map of process tables. Update several statistics, PG stat all tables, etc. It is assumed that readers are familiar with the following terms: dead tuples, freezing transaction ID, free space map, and the clog. If you are not, refer to Chapter 5. The visibility map is introduced in section 6.2. The following pseudocode describes vacuum processing. 1. Get each table from the specified tables. 2. Acquire share update exclusive lock for the table. This lock allows reading from other transactions. 3. Scan all pages to get all dead tuples and freeze old tuples if necessary. 4. Remove the index tuples that point to the respective dead tuples if exists. 5. Do the following tasks, steps 6 and 7, for each page of the table. 6. Remove the dead tuples and reallocate the live tuples in the page. 7. Update both the respective free space map and visibility map of the target table. 8. Truncate the last page if the last one does not have any tuple. 9. Update both the statistics and the system catalogs related to vacuum processing for the target table. 10. Update both the statistics and the system catalogs related to vacuum processing. 11. Remove both unnecessary files and pages of the clog if possible. This pseudocode has two sections, a loop for each table and post-processing. The inner loop can be divided into 3 blocks. Each block has individual tasks. These 3 blocks and their post-process are outlined in the following. (6.1.1) The first block. This block performs freeze processing and removes index tuples that point to dead tuples. First, Postgres scans a target table to build a list of dead tuples and freeze old tuples if possible. The list is stored in maintenance work mem in local memory. Freeze processing is described in section 6.3. After scanning, Postgres removes index tuples by referring to the dead tuple list. This process is internally called cleanup stage. Needless to say, this process is costly. In version 10 or earlier, the cleanup stage is always executed. In version 11 or later, if the target index is B-tree, whether the cleanup stage is executed or not is decided by the configuration parameter vacuum cleanup index scale factor. See the description of this parameter in details. When maintenance work mem is full and scanning is incomplete, Postgres proceeds to the next tasks, steps 4 to 7, then goes back to step 3 and proceeds the remainder scanning. 6.1.2 Second block. This block removes dead tuples and updates both the free space map and visibility map on a page-by-page basis. Figure 6.1 shows an example for moving a dead tuple. Assume that the table contains 3 pages. Focus on the 0th page, the first page. This page has 3 tuples. Tuple 2 is dead. In this case, Postgres removes tuple 2 and reorders the remaining tuples to repair fragmentation, and then updates both the free space map and visibility map of this page. Postgres continues this process until the last page. Note that unnecessary line pointers are not removed and they will be reused in future. Because if line pointers are removed, all index tuples of the associated indexes must be updated. 6.1.3 The third block. The third block updates both the statistics and system catalogs related to vacuum processing for each target table. Moreover, if the last page has no tuples, it is truncated from the table file. 6.1.4 Post-processing. When vacuum processing is complete, Postgres updates both several statistics and system catalogs related to vacuum processing, and removes unnecessary parts of the clog if possible. Vacuum processing uses ring buffer, described in section 8.5. Thus, process pages are not cached in the shared buffers. (6.2) Visibility map. Vacuum processing is costly. Thus, the visibility map was introduced in version 8.4 to reduce this cost. The basic concept of the visibility map is simple. Each table has an individual visibility map that holds the visibility of each page in the table file. The visibility of pages determines whether each page has dead tuples. Vacuum processing can skip a page that does not have dead tuples. Figure 6.2 shows how the visibility map is used. Suppose the table consists of 3 pages, and the 0th and 2nd pages contain dead tuples, and the first page does not. The visibility map of this table holds information about which pages contain dead tuples. In this case, vacuum processing skips the first page, or page 1, by referring to the visibility map's information. Each visibility map is composed of 1 or more 8 kilobyte pages, and this file is stored with the VM suffix. As an example, one table file whose rel file node is 1875.1 with free space map 1875.1_FFSM and visibility map 1875.1_VM files shown in the following. Six point 6.2.1 Enhancement of visibility map. The visibility map was enhanced in version 9.6 to improve the efficiency of freeze processing. The new visibility map shows page visibility and information about whether tuples are frozen or not in each page. Section 6.3 Freeze processing. Freeze processing has 2 modes, and it is performed in either mode depending on certain conditions. For convenience, these modes are referred to as lazy mode and eager mode. Concurrent vacuum is often called lazy vacuum internally. However, the lazy mode defined in this document is a mode how freeze processing performs. Is a mode when freeze processing performs. Freeze processing typically runs in lazy mode. However, eager mode is run when specific conditions are satisfied. In lazy mode, freeze processing scans only pages that contain dead tuples using the respective visibility maps of the target tables. In contrast, the eager mode scans all pages regardless of whether each page contains dead tuples or not. It also updates system catalogs related to freeze processing and removes unnecessary parts of the clog if possible. 6.3.1 Lazy mode. When starting freeze processing, Postgres calculates the freeze limit transaction ID and freezes tuples whose tx_min is less than the freeze limit transaction ID. The freeze limit transaction ID is defined as follows. Freeze limit transaction ID equals the oldest xmin minus vacuum freeze min age, where oldest xmin is the oldest transaction ID among currently running transactions. For example, if 3 transactions, transaction IDs 100, 101, and 102, are running when the vacuum command is executed, oldest xmin is 100. If no other transactions exist, oldest xmin is the transaction ID that executes this vacuum command. Here, vacuum freeze min age is a configuration parameter, the default of 50 million. Figure 6.3 shows a specific example. Here, Table 1 consists of 3 pages, and each page has 3 tuples. When the vacuum command is executed, the current transaction ID is 50,002,500, and there are no other transactions. In this case, oldest xmin is 50,002,500. Thus, the freeze limit transaction ID is 2,500. Freeze processing is executed as follows. The 0th page, the page at index 0, 3 tuples are frozen because all tx min values are less than the freeze limit transaction ID. In addition, tuple 1 is removed in this vacuum process due to a dead tuple. Page at index 1. This page is skipped by referring to the visibility map. Page at index 2. Tuple 7 and 8 are frozen, and 7 is removed. Before completing the vacuum process, the statistics related to vacuuming are updated, e.g. PG stat all tables, n live tup, and dead tup, last vacuum, vacuum count, etc. As shown above, the lazy mode might not be able to freeze tuples completely because it can skip pages. 6.3.2 Eager mode. The eager mode compensates for the defect of the lazy mode. It scans all pages to inspect all tuples in tables, updates relevant system catalogs, and removes unnecessary files and pages of the clog if possible. The eager mode is performed when the following condition is satisfied. PG database.dat frozen xid is less than the oldest xmin minus vacuum freeze table age. In the condition above, PG database.dat frozen xid represents the columns of the PG database system catalog and holds the oldest frozen transaction ID for each database. Details are described later. Thus, we assume that the value of all PG database.dat frozen xid are 1821, which is the initial value just after installation of a new database cluster in version 9.5. Vacuum freeze table age is a configuration parameter with default 150 million. I thought it was default 50 million. Vacuum freeze min age. Vacuum freeze table age. Alright. Different params. Figure 6.4 shows a specific example. In Table 1, both tuple 1 and tuple 7 have been removed. Tuple 10 and tuple 11 have been inserted into the second page. When the vacuum command is executed, the current transaction ID is 150,002,000, and there are no other transactions. Thus, the oldest xmin is 150,002,000, and the freeze limit transaction ID is 100,002,000. In this case, the above condition is satisfied because 1821 is less than 2,000. Therefore, the freeze processing performs in eager mode as follows. Note that this is the behavior of version 9.5 or earlier. The latest behavior is described in section 6.3.3. Freezing old tuples in eager mode, version 9.5 or earlier. The page at index 0, the tuple 2 and 3 have been checked even though all tuples have been frozen. Page at index 1, 3 tuples in this page have been frozen because all tx min values are less than the freeze limit transaction ID. Note that this page is skipped in lazy mode. Page at index 2, tuple 10 has been frozen, tuple 11 has not. After freezing each table, the PG class rel frozen XID of the target table is updated. The PG class is a system catalog, and each PG class rel frozen XID column holds the latest frozen XID of the corresponding table. In this example, Table 1's PG class rel frozen XID is updated to the current freeze limit transaction ID, that is 100,000,000,2000, which means that all tuples whose TX min is less than 100,000,000 and 2,000 in Table 1 are frozen. Before completing the vacuum process, pgdatabase.datFrozenXID is updated if necessary. Each pgdatabase.datFrozenXID column holds the minimum PG class rel frozen XID in the corresponding database. For example, if only table 1 is frozen in eager mode, the pgdatabase.datFrozenXID of this database is not updated because the PG class rel frozen XID of other relations, both other tables and system catalogs that can be seen from the current database, have not been changed. If all relations in the current database are frozen in eager mode, the PG database .frozen XID of the database is updated because all relations PG class rel frozen XID for this database are updated to the current freeze limit transaction ID. Figure 6. Relationship between PG database .frozen XID and PG class rel frozen XIDs. Only table 1 is frozen in eager mode. It's the minimum PG class rel frozen XID. System catalogs. All tables and system catalogs in the database in the test DB are frozen in the eager mode. How to show PG class rel frozen XID and PG database.frozen XID. In the following, the first query shows the rel frozen XIDs of all visible relations in the test DB database, and the second query shows the PG database.frozen XID of the test DB database. So we do a vacuum of table 1, then select n.nsp name as schema, c.rel name as name, c.rel frozen XID from pgcatalog.pg class c, left join pgcatalog.pg namespace n on n.oid equals c.rel space name, rel namespace, where c.rel kind in r, comma, empty space, and n.nsp name, it's not equal to information scheme, and n.nsp name, not like starting with pg toast, and pgcatalog.pg table is visible c.oid. Order by c.rel frozen XID, text, big int, descending. Schema, name, rel frozen XID. Freeze option. The vacuum command with the freeze option forces all transaction IDs in the specified tables to be frozen. This is performed in eager mode. However, the freeze limit is set to oldest xmin, not oldest xmin minus vacuum freeze min age. For example, when the vacuum full command is executed by transaction ID 5000 and there are no other running transactions,
Oldest xmin is set to 5,000, and transaction IDs that are less than 5,000 are frozen. 6.3.3 Improving freeze processing in eager mode. The eager mode in version 9.5 or earlier is not efficient because it always scans all pages. For instance, in the example of section 6.3.2, the page at index 0 is scanned even though all tuples in its page are frozen. To deal with this issue, the visibility map and freeze process have been improved in version 9.6. As mentioned in section 6.2.1, the new visibility map has information about whether all tuples are frozen in each page. When freeze processing is executed in eager mode, pages that contain only frozen tuples can be skipped. Figure 6.6 shows an example. When freezing this table, the page at index 0 is skipped by referring to the visibility map's information. After freezing the first page, associated visibility map information is updated because all tuples of this page have been frozen. (6.4) Removing unnecessary clog files. The clog, described in section 5.4, stores transaction states. When PG database dat frozen xid is updated, Postgres attempts to remove unnecessary clog files. Note that corresponding clog pages are also removed. Figure 6.7 shows an example. If the minimum PG database dat frozen xid is contained in the clog file 0002, the older files 0000 and 0001 can be removed because all transactions stored in those files can be treated as frozen transaction IDs in the whole database cluster. PG database dat frozen xid and the clog file. The following shows the actual output of PG database dat frozen xid and the clog files. So select dat name dat frozen xid from PG database. (6.5) Auto vacuum daemon. Vacuum processing has been automated with the auto vacuum daemon. Thus, the operation of Postgres has become extremely easy. The auto vacuum daemon periodically invokes several auto vacuum worker processes. By default, it wakes every 1 minute, defined by auto vacuum nap time, and invokes 3 workers, defined by auto vacuum max works. The auto vacuum workers invoked by the auto vacuum perform vacuum processing concurrently for respective tables gradually with minimal impact on database activity. How to maintain auto vacuum. Refer to tuning auto vacuum in Postgres and auto vacuum internals. 6.6 Full vacuum. Although concurrent vacuum is essential for operation, it is not sufficient. For example, it cannot reduce table size even if many dead tuples are removed. Figure 6.8 shows an extreme example. Suppose that a table consists of 3 pages, and each page contains 6 tuples. The following delete command is executed to remove tuples, and the vacuum command is executed to remove dead tuples. Delete from table where ID mod 6 does not equal 0. And then vacuum. The dead tuples are removed, however the table size is not reduced. This is both a waste of disk space and has a negative impact on database performance. For instance, in the above example, when 3 tuples in the tables are read, 3 pages must be loaded from disk. To deal with this situation, Postgres provides the full vacuum mode. Figure 6.9 shows an outline of this mode. So first, create new table file. When the vacuum full command is executed for a table, Postgres first acquires the access exclusive lock for the table and creates a new table file whose size is 8 kilobytes. The access exclusive lock does not allow access. Second, copy live tuples to the new table. Postgres copies only live tuples within the old table file to the new table. Finally, remove the old file, rebuild indexes, and update statistics, free space maps, and visibility maps. After copying all live tuples, Postgres removes the old file, rebuilds all associated table indexes, updates both the free space map and visibility map of this table, and updates associated statistics and system catalogs. The pseudocode of the full vacuum is shown below. For each table, acquire the access exclusive lock for the table, create a new table file, and then for each live tuple in the old table, copy the live tuple to the new table, and freeze the tuple if necessary. Then remove the old table file, rebuild all indexes, update the free space map and visibility map, update statistics, and then release the access exclusive lock. And then finally, remove unnecessary clog files and pages if possible. 2 points should be considered when using the vacuum full command. First, nobody can access, read, write the table when full vacuum is processing. 2. At most, twice the disk space of the table is used temporarily. Therefore, it is necessary to check the remaining disk capacity when a huge table is processed. When should I do vacuum full? Unfortunately, there's unfortunately no best practice when you should execute vacuum full. However, the extension PG free space map may give you good suggestions. The following query shows the average free space ratio of the table you want to know. So create extension PG free space map, and then select count star as number of pages, PG size pretty cast average available as big int as average free space size, and then round 100 times the average available divided by 8 kilobytes, to 2 decimals as average free space ratio from PG free space and then the table. As the result above, you can find that there are few free spaces. If you delete almost tuples and execute vacuum command, you can find that almost pages are spaces ones. Delete from account where AID mod 10 does not equal 0 or AID is less than 100. Vacuum accounts. The following query inspects the free space ratio of each page of the specified table. Select round 100 times available divided by 8 kilobytes, round that to 2 decimal points as free space ratio from PG free space accounts. After executing vacuum full, you can find the table file has been compacted. Vacuum full accounts. Select count, the same query as above. Before it was 10 times that, right? So we did this. Yes. Sup, yo? Hey, I'm about to jump off to go do the work thing, but thanks for hanging out. I'll see you later.